Good day, everyone. Welcome to Chemistry with Professor John. This is the homework and quick review for Chapter 1 to Chapter 3, Organic Chemistry 1. That's Chem 281. Okay. The key concept and skills from Chapter 1 and 2 are drawing Lewis structures, and our main focus will be on organic molecules. Here I'm showing you guys the expanded structure you got 2-methylbutane, expanded structure 2-methylbutane, where you see everything shown, carbon hydrogen bond, carbon carbon bond, everything. It would take too much time to draw that every single time, so we decide to condense on each carbon. Okay, so you notice the first one is C and 3 hydrogens. That's C and 3 hydrogens. But you keep following, okay? The next one, CH2, and so on and so forth. So those are called condensed structure or formulas. This one right here would be expanded structure or formula. All right. Now, here's a few examples. Draw the condensed and line structures for the following compounds. And there might be more than one structural isomers. So CH3, the condensed will be C3, C3H8, CH2, CH3. If you count, it'll be 1, 2, 3 carbon, 3 plus 2 plus 3, that's 6 hydrogens. That's 8 hydrogens. If you do the line formula, it will be 1 carbon, 2 carbon, 3. If you're not sure, label the carbon. Okay, that's the only way to draw the structure. So that's the only isomers. Okay. Now for C4H10, okay, we can just skip the condensed formula and do the line formula because it's a lot faster. So that's 1, 2, 3, 4. I'll be able to recognize number 1, that's a CH3. Notice carbons need 4 bonds. And we're talking about 4 single bond or a double bond and 2 single, any of those combinations. A triple bond and a single bond, that's so on and so forth. Or even a double and 2 single. Any of those combinations will work. All right. Now, okay, so we got CH3, CH2, because it's got 2 already, so it's only need 2 hydrogens. CH2 and then CH3. So that make it a 3 plus 2, that's 5. Plus 2, that's 7. Plus 3, that's 10. So that's perfect. Now watch. Instead of drawing number 4 the same, we're going to break number 4 and we put it right in the middle. That will make it another isomers, known as structural isomers. So in order to draw a structural isomers, it has to be different bonding sequence. Therefore, it has to be different molecules. But they share the same formulas, molecular formulas. Okay, so that's 1, 2, 3, 4. And it seems like that's it. There's only two possible way to draw the structure from that given formula. So therefore we got 2 structural isomers. Moving on, C3H6. Now we have 3 carbon, but we only have 6 hydrogens. So that's mean if we leave it at a single bond, we would have 8, like the previous one right here. But this time we have 2 hydrogens short. Therefore, the best way is to make a double bond. But we can also make the enclosed structure because each carbon would have 2 hydrogens. That make it a 6. So we can do that. So we got 2 different structural isomers. One is an alkene. That's another thing we need to know, the functional group, and the other one is a cyclopropane. Okay, but we'll get to the name later in chapter 3. Now we get to C3H4. We're losing another 2 hydrogens. So we can do a triple bond, which is a straight line, 1, 2, 3. And or we can do a cyclopropane with a double bond. All right. Okay. The second big concept that we need to know is resonance. So the first one was structural isomers. And as we did here, structural isomers. And the second one's big concept will be resonances and be able to tell the difference. Okay, resonances have different placements of the pi bond, okay, and the valence electron, the lone pairs. They have the same bonding connectivity, same 3-dimensional shape. Okay, so what's the clue? How do we draw? So these are essentially the same molecules or ion. They just happen to have 2 different way. That's acetate ion, 2 resonant forms, 2 different valid Lewis structure for the same ions or molecules. Now isomers are different. You got 2 different molecules, 2 different structure, share the same molecular formulas. Just imagine you have the same amount of material, wood for example, and you can use the same amount of wood to build a table. You can use that same amount of wood to build a chair. That would be called isomers. Well, I know it's weird. The chair and the table, they look completely different. Yes, they are different, but they come from the same material, wood. Okay, that's structural isomers. Now, resonance are different. Resonance are same. Okay, the same molecules or ion, just different way to draw the structure. The analogy would be you can sleep with both of your arm up, above your head, or down. Okay, that would be isomers. Maybe that would be, that would be resonances, but maybe conformations. That's actually better. Okay, which we're gonna get into it in chapter 3. Okay, now, but anyway, to draw resonances, use arrow to show the movement of the pi bond and the lone pair. That's the key, okay? The pi bond. So we gotta have a double bond or a triple bond. And nice to have a charge, like negative or positive, but it's not required. But if you have a molecule with all single bonds, there's no way we can get a resonance. Okay. All right. So here, Very good example from the books. We got oxygens with 3 lone pair. We're going to move 1 lone pair to make a double bond. And then the green oxygens with 2 lone pair, and we're going to convert the pi bond, which is one of the double bonds, one bond of the pi bond. We can convert that bond into a pair. So you end up with a green one with 3 lone pairs, green oxygens, and that's carried a negative. And the red one become neutral because it get rid of the lone pair. Okay, and those step happens quickly. Okay, so we got 2 different resonances, but they still the same ion and behave similarly. It does happen that you have 2 different resonances. One is more dominant than the other, just because it's more stable. The way the bonds and the lone pairs are built, it's just more stable. So it's more dominant, like 99% versus 1%. Well, in this case, you have these 2 resonances. These 2 resonances are equally stable because each of them has a double bond O and a single bond oxygens with a negative on the oxygens. So they're equally favorable, okay? But if you have like a C double bond O, CH3 and CH3, and you move the pi bond to make a lone pair on the oxygen that make it a negative, and the carbon missing a bond become positive. In this case, this resonance is more favorable because it's neutral. It satisfies the octet rule. The other one, carbon positive, does not satisfy the octet rule. Okay, and there are charges, so it's not as stable as the one on your left. Okay, so that happens when you have multiple resonances, and one is more stable than the others. Okay, back to structural isomers. We got, and also known as constitutional isomers. Here's some more examples. Same molecular formula, but different bond connectivity. Now we have C4H10. So we have a straight butane and we have a branch. Okay, and we did that earlier. They could be functional. Could be functional group is so important. If we have a hint that do 2 isomers that one is alcohol and one is ether, we know, because if it's an alcohol, we know it's an OH. Okay, so if someone say draw the isomers, the alcohol isomers, then we know we have to have OH, and the rest will be CH3 and CH2. But if someone asks us to do draw the ether isomers, then we know oxygen's got to be in the center. It doesn't have to be the same on both sides, but it has to be carbon on both sides. In this case, we split it up into 2 metal on both sides. And then another scenario will be to draw isomers, structural isomers, would be place the functional group in different carbons. Okay, so in this case, if someone asks us to draw all amine isomers, amines means NH2, so we know we gotta have NH2, and one we connect to the middle carbon, and the other one we connect to the right carbon or the left carbon. Okay, if you put the NH2 to the other side, that will be the same molecules. because just simply a flip. Okay, so that means we have two different isomers, structural isomer for this case. Okay, and here's are the name of the non-cyclic or straight chains alkanes, and we got 10 of them. Well, in this case we have more, 10, 11, 12, 13, 14, 13, and 20 and 30. So know this, because these are the foundations of fundamental molecules of all other alkanes. All right, example. Now, like I mentioned earlier, if we know the concept of functional group, it helps a lot. And esters are one of the popular ones. So if someone asks us to do 2 isomeric ester, then we know we need to focus on ester, because this molecule could be anything, okay, other than ester. So we know ester has to have a double bond O and O. Doesn't matter which side. So that's 1 carbon and 2 oxygen taken care of. So we got 4 carbon left. Okay, so we just keep connecting. For example, we got 4 carbon, so maybe we can do 1, 2, 3 on one, and then 1 on the other one. That make it a 4. And I'll double check, and that's C double bond O. So 1 on the right, 3 on the left, that's 4, and 1 carbon on the double bond O, that's 5. So you got 5 carbon. If you look at number 1 here on the right, that's a CH3. On the left, it's a CH2, CH3, that's 7. 7 plus 3, that's 10 hydrogens. Okay, so that's perfect. That's exactly what we need. Now, watch. We're going to move the other isomers. We're going to put 2 carbon on one side, 1, 2. That'll make it a 4 carbon plus the carbon of the double bond O, that's 5. And if you check the hydrogen, there's CH3 on CH3 and CH2, that's 5 hydrogens, the same on the right side. So that's perfect. So we got 2 different ester. So always count the hydrogen and carbon and oxygens, so on and so forth, to make sure it matches with the formulas given. Okay, now we got nitrile. Nitrile is C triple bond N. Okay, so we got to have that. And then we got 7 hydrogens. Okay, so keep going. So we got 4. So 1, 2, 3, and sometimes condensed formula is easier to do. So you got 3 plus 2 plus 2, that's 7. So perfect. And then CN. Okay, now this one is the same as 1, 2, 3, 4. So that's 1, 2, 3, 4. Or you can do, you got 1, 2, 3, and the carbon of the CN make it a 4. So we got 2 different isomers. Okay, as requested. Okay, in the live formula. In this case, the condensed formula doesn't take that much time to draw, to write, and it's easy to see. So whichever is convenient for you guys. Okay, 2 isomers, alcohol. Okay, that's a good hint, right? So this is a good practice to draw different structural isomers, and also to review the functional group, alcohol. So alcohol, we gotta have OH. So we got 3 carbon, OH. And make sure you number it, 1, 2, 3. And that's not a carbon. That one is not a carbon. That's an oxygen, okay? So that's not a 4. It's not a carbon and then oxygen. All right. Okay, so we got one like that, and we got the other one like this. That's 2 isomers. Okay, C4 is 9Br, so that's 4. So that's 1, 2, 3, 4, and then we're gonna put the Br on that. And always double check. CS2, 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 that's 6 plus 3, that's make it a 9. Right there, CS2, 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 that's 6 hydrogens. CS3, that's make it 9 hydrogens. Perfect. All right, now we can move the Br to carbon number 2. That make it another isomer. Okay, now watch. We're gonna move number 4 to number 2 as well. So there's no number 4. It's moved right here. That's number 4. Okay. Now, for the second structure, we can also, for the last structure, we can also move the Br to outside to the carbon number 1, back to number 1. And that create a different structure. Nothing like the first 3. So we're gonna call it 4 isomers. Unless you guys can come up with another one that's different, okay? Okay, number 3. Draw all possible line structure formula for C5H10. Notice 5H10. So we can only have 10. So that means if you do 5, that'll be a CS3, CS2, that's 5. CS2, that's 7. And then if you do CS3, 2, that's 9 plus 3, that'll make it a 12, right? That's CS3. That's a CH2. That's a CH2. CH2, and that's a CH3. Okay, that should be too many. That'd be like 3 plus 2 plus 3, 2. Okay. Plus CH2 plus 3. So that's like, if you double check, it's like 12. It's 3 plus 2 plus 2 plus 2 plus 3. That's 12. That's too many. We only have 5. Okay. So that's not good. So we need to reduce it. Okay. So that should be a CH2, and that should be a CH. So that should be a CH. So we're gonna put a double bond, and that's a CH2. So that make it a 1, and that make it a 2, and that make it a 10. So it's perfect. So we gotta have a double bond. That's my point. But it took us a while to figure it out. There's no hint. If it just say alkene, then we know it's got a double bond. Okay, so, and then you guys can go from there. You know, you can do double bond from the inside here. So that's, you know, changing a double bond. That's already give you different isomers. Now let's start making branches. You know, instead of there, you just stick it there, and so on and so forth. Okay, There should be a couple more. Finally, one here on this branch, and we're going to stop right here. And the other part is going to be on the next video. Okay, benzoic acid. So if you look up the structure of benzoic acid, you can draw it like this. Double bond OOH, that's benzoic acid. So that's benzoic acid. It's an acid, okay? And then you do conjugate base, mean you need to take out the hydrogens. So that's the benzoate, which is a conjugate base. So that's a CB. Conjugate base, that's an acid. Now, resonances. That's going to be fun. Okay. Now I'm going to go ahead and erase the circle because to do benzoic acid resonances, it's better to show the double bonds. So the first one is to make the double bond O. The other two double bonds are the same, but notice this one right here become negative because the double bond, which is the pi bond, turn into the lone pair. And then you can keep going from there. Double, make that into a minus. So you got yourself another resonance, and if you do it again, you get yourself into another resonance. There you go. That should be it, okay? So those are the resonances. All right. So those are the thing that, those are the concept and skill that we need to know for chapter 1 and chapter 2, and you should be good. Other than that, we got bond polarity, intermolecular forces. You know, sometimes we run into those to explain the boiling point and, you know, other physical properties. But what we've done so far, the drawing isomers and resonances, these are good. These are a good start. Okay. Now, next video we're gonna go over the alkanes, from naming to a couple simple reactions and structural analysis. Okay. All right. Thank you for watching, everyone.